Welcome to lesson 2 from chapter 9, Pure Mathematics, Differentiation. And today we're going to look at the chain rule. And this is a method that we're going to use extensively from now on. And it's quite, when I say extensively, it is actually quite extensive. There's many ways this can be used. And as a result, we're going to split lesson 2 into several parts, okay? Just so we can address as many different variations as possible of how this can be applied. So there's a few things we need to know before we get started using the chain rule. We need our derivatives from the previous lesson that we came across, that we did from first principles. There's also the inverse function of the exponential function and the natural logarithm, as in they are inverse functions. So if you compose the two functions together, it is the same as doing nothing to the original input. And we've also got here the laws of indices. So we're going to be revisiting these things quite a bit. Now, before we explain what the chain rule is, I'm just going to give you a few questions to do in the warm-up, which will hopefully lead you into the idea, and you can see the real utility of using this in future examples. So please pause the video and have a go at the 4 warm-up questions, please. Okay, and let's have a look at the solutions. All right, so for question 1, we're asked to expand and simplify. Okay. Nothing too disconcerting on the face of it. It's just a case of we've got to write everything out. So a good thing to do, and notice, of course, how awkward it is. We've got a power 3 here, and we're doing this for a particular reason. It's to show you again, as I mentioned previously, the utility of the chain rule later. So we're going to write it out. We're not differentiating or anything. We're just going to write it out. So y would be the product of 2x squared plus 1, and then the same thing twice over. So 3 of those brackets. So 2x squared plus 1 cubed, as stated. So a good thing to do would be just to focus on 2 brackets at a time. So I'm going to focus on brackets 2 and 3 here, the middle and the outer, and we're going to multiply those 2 together first. Now, if I do that, of course, we're going to get the following. So again, this is a good exercise in algebra skills, isn't it? 2x squared plus 1. Now, and let's open up a big square bracket and let's multiply out what's inside. So 2x squared multiplied by itself is obviously going to be 4x to the power 4 plus 2 lots of 2x squared. So that's going to be 4x squared. So 2x squared plus 2x squared, and then plus 1. Okay. And just double check that, make sure you're happy with what you've done there. Right, okay, now we've expanded 2 of the brackets, we can now bring in the 3rd bracket and multiply through by 2x squared and 1. You might have a different way of doing this. This is just my approach. So let's multiply everything by 2x squared first. So 2 times 4 is obviously 8. And laws of indices, of course, just be careful with this. That's why I put them up at the top. X squared multiplied by x to the power 4. I probably would forgive you if you wrote x to the power 8. But remember, of course, laws of indices state that we have to add the powers together. So this is going to be 8x to the power 6. Okay, and let's continue. Multiply the second term by 2x squared, so that's going to be plus 8. And then again, we've got to add the powers. So x squared multiplied by x squared will give us x to the power 4. Okay, and then multiply 1 by 2x squared. That's obviously just going to be 2x squared. Okay, so we've done the first bit. So that's multiplying the second bracket, the green square brackets by 2x squared, and now we're going to multiply everything inside by 1. So I'm moving on onto this part now, multiply all this stuff in here by 1. And a good thing to do is to line up as you would do in a kind of additional column multiplication situation. If you line up the powers, and then we can add the powers together by collecting like terms. So the first one, of course, is going to be 1 multiplied by 4x squared. Sorry, 4x to the power 4. So I'm going to put that there, 4x to the power 4. So effectively, this is the x to the power 4 column, like that. And then do the same thing for the other two. So that's going to be plus 4x squared. Okay, and then plus 1. All right, and then we add all this together. So we're going to get 8x to the power 6. All right, plus 12x to the power 4 plus 6x squared plus 1. Okay, so that's the final expression. It was quite a task, wasn't it, to do that? Now, let's suppose we want to differentiate this. Now, as it stood originally, y equals a bracket, not a massively complex bracket, but a bracket nonetheless. If you want to cube this bracket and then obviously differentiate it, at the moment, all we can do is what we've done already, is to multiply everything out and then differentiate term by term. Okay, so the next question is a show that, isn't it? So question 2, it says, using your expansion from question 1, show that the derivative with respect to x is as follows. Okay, well, we just verify it, don't we? It'll just be a case of writing everything out again, but checking that the technique is indeed the case. It does work. So the first thing I need to do is to take the 6 down and multiply that by the 8. Okay, and then I have to subtract 1 from the power, so that's going to be 5. Okay, second term, I have to bring down the 4. So if not sure where I'm looking, so I'm looking at this term now. So bring down the 4. Okay, that multiplies the 12, and then we have to take 1 off the power. 1 off the power of x, of course, so that's going to be 3. Next step, okay, so the next term along, that's 6x squared, so it's going to be 2's coming down now. Multiplying the 6. Okay, and then I have to take 1 off the power of x, so that's going to be x power 1. And then the constant term on the end, of course, this would just disappear. Okay, it doesn't have any effect on the rate of change of your function. Okay, right, so let's see if this works. So just a case of multiplying together. 6 8s are of course 48, x to the power 5. 4 times 12 is again 48, x cubed, and 2 lots of 6 is of course 12, so that's 12x. Right, so that seems to check out, doesn't it? It looks like we've expanded successfully and we've differentiated successfully. Everything seems to follow. Now for question 3, we take the results. This is the derivative from question 2, and we're going to factorize it fully. So let's see what we can actually factorize out of this. Well, we can see that there are multiples of 12 all the way along. Okay, which is good. And we've also got an x term we can take out. So let's start with that. So let's start with 12x. And we'll see if there's any further factorization in a moment. So that's going to be 12x, and let's see what we have left over. Well, that's going to be 4x to the power 4, isn't it? Okay, and we've also got plus 4 again, x to the power 2, and then 12x, that's going to be plus 1. All right. Now, the question is, does this factorize again? Let's have a think about that. Well, this is quite interesting, isn't it? If you cast your eyes over worked example 1, this may look familiar to you, okay? Now, where did we see this? Well, this was what we got when we multiplied 2x squared plus 1 by itself. So that part is the same as 2x squared plus 1 multiplied by 2x squared plus 1, okay? And the only difference, of course, is now we've got the 12x at the front multiplying the whole thing. So that's quite interesting. So I could actually write this even better. I could say, all right, this is going to be 12x multiplying 2x squared plus 1 all squared. And remember, of course, that represents the derivative of the function that we saw earlier. So we know that if I take the derivative of what we started off with, which was, I'll write it in green, 2x squared plus 1 to the power 3. If I differentiate that, once we've made the final derivative look nice and it's fully factorized, we get this result. And I would just spend a moment, just sort of cast your eyes over this and see if you notice anything interesting about it. Okay, there'll be more to follow about this, but there is quite an interesting relationship between the derivative and the function. Okay, it's not random, is it? There's the 2x squared plus 1 features in both. So what is the link? Okay, we'll explore that later. Now, question 4. We're given a function defined harmonically. We've got sine x plus cos x, like that, and we have to find the x coordinate of each stationary point. And you'll notice we've got an interval to consider here. So let's do that. We can differentiate directly. So remember the notation, f dash x if it's a function, or g def x if the function is g of x. And we do it term by term. Well, if we differentiate sine, of course, use the result from earlier, we get cosine of x, cos x. And if we differentiate cos x here, we get negative sine. So it's going to be negative sine x. Okay, so that's the derivative. And we're told, or we are interested in stationary points. Stationary points, what do we know about stationary points? Well, we know that the derivative has to be 0. So let's state that. Show off to the examiner what you know. So at stationary points, the derivative f dash x must equal 0. So we set our derivative equal to 0. So therefore, cos x subtract sine x must equal 0. So the question is, how do we solve this? Well, we can use our trusted trig identities for this. A good thing to do, if you see cos x and sine x, and you know it's all equal to 0, a good thing to do is to try and convert this into tan x. And we can do that, of course, by dividing everything that you can see by cos x. All right, and it's valid because these are identities, okay? They're identities, so they're valid for all x, so it's not cheating. So cos x over cos x is, of course, going to be 1. And then sine x over cos x is going to be tan x. And that's equal to 0. Obviously, if you divide 0 by cos x, just 0. Now then, let's rearrange this. In fact, I should probably state that as well. Otherwise, it's wrong, isn't it? Okay, we're dividing everything by cos x. Okay, let's rearrange. So let's make tan x the subject now. So we now have by adding tan x to both sides. So 1 is equal to tan x. And we just have to solve this equation in the interval given here. Okay, well, we can use a principal angle. Do we have to, well, we have to use radians, of course. So let's find our principal angle. All right, so we use the inverse tan button on the calculator, or if you know it, even better. So the inverse tan of 1. So it's going to be 45 degrees, but as you know, in radians, that's pi over 4. Okay. So you just check that on your calculator. So that's our principal angle. So the question is, where do we put this on our cast diagram? Well, cast diagram, let's draw it here. C, A, S, and T. Let's put the angles on. 1, as given to us in the question, the number 1, which is equal to tan x, is a positive number. So we look where tan is positive, so T and A, and we add our angle to those quadrants. So that's pi over 4. And pi over 4, always to the horizontal, of course. And we can find our answers. Now, in this case, we only need the x coordinates, which is handy. It means we don't need to substitute x into the function. We're just happy with the x coordinates. Okay, so I'll just box this off so we've got a bit of space. So x is going to equal the first reading, which is pi over 4. Remember that we go in that direction. That's the positive direction from 0. And the second angle is pi over 4 more than pi. So that's going to be 5 pi over 4. So in other words, 4 pi over 4, which is pi, plus pi over 4, which is 5 pi over 4. So those are our 2 x coordinates. Okay, so that concludes the warm-up. Now, there is another way you could do this, if you want to try it. We talked extensively about harmonic functions in chapter 7. Now, one thing you could do, if you want to try it, is rewrite this function using a single identity. So, for example, you could use r sine of x plus alpha, something like that, and rewrite the function in that form and solve the equation that way. And maybe just try it as an exercise, see if you get the same answers of pi over 4 and 5 pi over 4 that we have down here. Okay, so just an interesting exercise for you, just to consolidate what you did in chapter 7. Okay, so that concludes the warm-up. All right, so to get us started, we're going to have a look at the idea of how to differentiate composite functions. And why do we want to do this? Well, it's because we may be confronted with a situation like this, where we'd want to differentiate y equals sine of 3x. Now, we know what the derivative of sine x is, so I'll just make a note of this. But we can't say any more than that at this stage. We know that the derivative of sine x is cos x. We did it from first principles, and we've been using this result. But we haven't talked about sine of 3x, or sine of 2x, or sine of 4x, or anything else more complicated. So how does that fit into this idea? Well, we actually need a different technique to address this. And what we're going to do is we're going to envisage that to form a function such as y equals sine of 3x would be to take the function sine x as we've got here, okay, but make a substitution for x, okay, and the substitution we'd clearly make would be to replace x with 3x. Now, what that essentially does is that creates a composition of functions, and we can write the composition as follows. So I can write y as a function of some other variable, which we're calling u, and this is a standard way of writing it, okay? So it's not something I've made up. Y equals sine of u, and then we also need to define u. Well, u would have to be 3x, okay? And then obviously when you substitute u into the first equation, if you like, so if we go back to this one, if I replace the u here with 3x, we of course get y equals sine of 3x. Okay, so that would be if we compose the functions. Okay, so this is what we call a composition of functions, and you know about this from the previous chapter 2, I believe, on functions. Okay, so how does this help us differentiate y equals sine 3x? Well, we can do it in the following way. Okay, and you can have a go at this yourself. What we could actually do is we could differentiate this function separately, and we could also differentiate this function separately. All right, and again, I'm just going to remove that. So if we're differentiating function, or let's call it equation 1, y equals sine u, then what are the variables? Well, clearly, we're going to be differentiating with respect to something. All right, so it's going to be dy by something. Now, the variable, though, in question is not x in this case, is it? The independent variable, I mean, is what I'm referring to. The independent variable is not x, it's u. So this is going to be dy by du. All right, and there's nothing wrong with that. We call it dy by dx simply because we're differentiating a curve, usually y, with respect to the variable x, okay? But we can call the variables whatever we like. We're not limited in that respect. So if I want to work out dy by du, I can apply the rule from the first lesson in this chapter, which I've given in the top right corner up here. So I can just use this now directly. But instead of obviously giving sine, cos x, my derivative is now going to be with respect to u. So this is going to equal cos of u. I'll do the u in orange so it's consistent. Okay. So I hope that makes sense. That's differentiating function number 1. Okay. Or equation 1. Now, if we differentiate equation 2, again, we've got different variables to consider. It's u as the subject, and the independent variable is x, okay, not u this time. So this time, we're going to have du by dx. We're going to differentiate u here with respect to x here. So let's do that. Now, if we differentiate u with respect to x, well, the differentiating 3x is just going to give us 3. Okay. So we now have 2 separate derivatives. We've differentiated y with respect to u in equation 1, and we've differentiated u with respect to x in equation 2. So our job now is to find out what the derivative dy by dx actually is. Okay, now before we put the derivatives together to find dy by dx, just want to go over what's happened just once again to make this absolutely clear. When we have equations of curves, things like sine and 3x like we have here, the independent variable is the variable contained inside the function, okay, which is the bit you differentiate, and that appears in the derivative on the bottom. Okay, so this is a curve written as with y as a subject as a function of u. So in this case, sine of u. And when we differentiate it, we call it dy by du. All right, and then the independent variable is there again. Now the dependent variable is the how it's written. It's the letter, if you like, that is the subject of the equation. So in this case, y. It's not always the case. We'll talk about that in later lessons. But for the moment, it's the variable that is the subject of your equation. So y equals sine u, and that appears in the numerator there. Okay, that's called the dependent variable. And we've got the same idea in equation 2. So the independent variable is what's contained inside the function. So it's like a function of x, like f of x. So in this case, it's u equals 3x. And once again, the independent variable appears on the bottom. And our dependent variable u appears in the top, the numerator of our derivative. So that's du by dx. Okay, I hope that makes sense. Now, what we have to do with these two results is we have to form dy by dx. So it says that we're going to construct dy by dx. Now, what I recommend we do, just to make this clear, if I want to construct dy by dx, then, and I've got two components here to use. I've got the derivative of equation 1 and the derivative of equation 2. So the first thing I need to make sure is that I have a dy in the numerator. Okay, that's the first thing, because my derivative on the left-hand side has a dy in the numerator also. So that's got to correspond. Now, if I have a look at what I've got over here on the left-hand side, what do I have to choose from? Well, I've got this derivative and this derivative. Which one has dy in the numerator? Well, okay, lo and behold, it's going to be the derivative of equation 1. So that means that I can write my first derivative as dy by du. Okay, but that's not what we wanted, is it? We need to get a dx on the bottom. How are we going to get a dx on the bottom? Well, we're going to have to bring in our second derivative for equation 2. Now that does have dx in the bottom. Okay. All right, and then I can put the du on top. And if I multiply them together, you'll notice something really interesting. So does this actually work? Well, if you look at the denominator, I've got dx there, that corresponds, but I've got this other variable du, which is in the way. But does it matter? Well, you'll notice we do have an equation here, because the du in the denominator and the du in the numerator simply cancel each other out. Okay. It's important not to think of these things as fractions, although the rules still apply. It still works. That these are derivatives, okay? But you can see that the du in the denominator and the numerator will cancel each other out. So that's how we can construct our dy by dx now. So if I do that, it's going to be dy by du. Okay, now that's cos u. Okay, multiplied by 3. Okay, so it still looks a bit odd, doesn't it? All right. Surely, if I've got a derivative with respect to x, then I should just have y's and x's, or just x's in this, I should say. So all this derivative should just be in terms of x. Well, I can do a couple of things here. I can write this as, well, I can put the 3 at the front, first of all, to make it look a bit nicer. So it's 3 cos u. But then I have to remember what u actually represents. So u here, I don't really want to keep that there because it's supposed to be dy by dx, and I have the wrong variable. But you'll remember, of course, that we defined u in equation 2, didn't we? Okay, it's right here. U is equal to 3x. So I can simply replace my u here with 3x, and lo and behold, I've got my derivative. So this is going to be 3 cos of 3x. Okay, and that's what the derivative of sine of 3x is. Okay, so we seem to have got to a reasonable looking answer there. So now we're going to do some examples, and then we're going to generalize our examples. So we found two derivatives from two different functions that were composed together to form the function that was given to us in the question. Now, when we use this technique where we differentiate two functions separately and then compose the derivatives together, this is called the chain rule, okay? Which is what we've just used. Now, for this example, example 1, we have sine of 2x in this instance. So I'm going to sort of give you a framework on how to do this, and then you can apply it in your own questions. And once you've got the hang of it, you won't need to use this in such detail. You'll be able to hopefully just write down the answers, but that will come with practice. So the first thing to notice is if I want to differentiate in example 1 sine of 2x, then I could define my function as y equals sine of something, but then my secondary function, the thing that is going to be composed with it, would have to be the 2x, because that's the part that I don't have a standard derivative for. I can't just find the derivative of sine of 2x directly at the moment. So we're going to call our first function y equals sine of u, like that. Okay, and for our second function, u would have to be 2x. And then when I compose them together, I get y equals sine of 2x. So maybe just make a note of that. So i.e. y is equal to sine of 2x when you compose them both together. So we'll call this one 1, and we'll call this one 2, and we'll differentiate them separately with respect to their respective variables. Okay, lots of respect going on there. So first of all, dy by du this time. Okay, because of the independent variable in this instance is u. And we use the standard result for differentiating sine. Okay, so if we differentiate sine of u with respect to u, then it's just going to be cos u. If I was differentiating sine of x with respect to x, that would be cos x. If I was differentiating sine of z with respect to z, it would be cos z. Okay, hopefully you get the idea. Now let's differentiate u with respect to x now. So this is going to be du by dx. Okay, once again, I'm just going to highlight those independent variables in the denominator. There they are. Okay, and if I differentiate 2x, that's a really simple derivative from last year. So that's just going to be 2. Okay, and to get dy by dx, I just have to compose the derivatives of 1 and 2 together. Okay, so when I say compose, it's a case of multiplying them together essentially. So dy by dx is going to be dy by du multiplied by du by dx. Okay, if you're not sure whether it's correct, just remember you want to create the cancellation in the numerator and the denominator of that new variable that you've created. Okay, that has to go. So we put them both together now. So this is going to be dy by du, which is cos u. All right, and then du by dx, which is 2. Okay, and let's make that look a bit nicer. So this is going to equal 2 cos, and I can do this in one step actually. I want to replace this u here with how it was defined. Well, it was defined as 2x, wasn't it, in equation 2 right here. That's how u is defined. So it's going to be 2 cos of 2x. All right. Okay, so that's example 1, and there's the derivative, 2 cos 2x. Now, you may have noticed a pattern happening. Okay, let's just make a note of what's just happened so far. So when we differentiate the first example, we had a look at sine of 3x when we set up this process, we got a derivative of 3 sine. No, we didn't. We got a derivative of 3 cos 3x. Okay. Similarly, in example 1 just now, we've done d by dx. We've differentiated with respect to x sine of 2x. Okay. And what did we get? Well, we got 2 cos 2x, didn't we? Okay, so the question is, what will happen if we differentiate more generally sine of kx? Put the k in red. Sine of kx. All right, where k is a real constant, just like what we've been using. So like 2, 3, or pi, or whatever it is. What would happen if we put a real constant in there? I'm sure you can anticipate what the answer is going to be. So maybe just write it in yourself, and then I will check with me on the video. Well, what's the pattern? Well, it looks like what's going on is, without applying the chain rule as we've done on the left-hand side, it looks as though what happens is we differentiate the sine function to get the cos function, as we saw from first principles. So it's definitely going to be a cosine. But it also looks as if the coefficient in front of the x seems to migrate to the front, okay, as well as a coefficient at the front of the function, without disturbing anything that's going on inside the function. Okay, so we retain the 3x or the 2x, whatever it is, inside the function, but that coefficient, the 3 or the 2 or whatever it is, seems to migrate to the front and multiply the whole function together. So we could probably anticipate what's going to happen with k. It's going to give us k multiplying the front of the function, and then we're going to get the cosine as the derivative of the sine, and then we're going to get the kx back inside the function. All right. So can we verify this using the chain rule? Okay, so that's my hypothesis. But in mathematics, you can't just, well, pattern spotting is important, but you have to be able to prove your result. So let's maybe just pause the video and have a go at proving this using the chain rule. Okay, and then I'll go through in a second. All right, so let's have a look what we would get. So I'll just box this off. So my two functions would be y is equal to sine of u. That would be my first function. We'll call that function number 1, or equation 1, I should say. And then we would have u is equal to kx, where k is just a constant, okay? Nothing to be afraid of. And let's differentiate them separately. So we would have dy by du, which would equal, the derivative of sine is, of course, cos. So this is checking out, isn't it? That's going to be cos u. And then du by dx. Okay. So k, like a constant, like 3 or 2 or 5, whatever it is, that's just going to leave us with k. When we compose these two together, i.e. by multiply those results, we can say that dy by dx would be the product of k and cos u. So that's going to be k cos of u, but we know that u is kx. So that's going to be k cos of kx. All right. You can even state in this step here that because it's a u in there, that's going to be cos of kx. You could probably do that there as well if you wanted to. Okay, so yeah, that does check out. So our hypothesis, just by looking at the pattern, does indeed work. So let's move on to example 2 now, and we see if we can generalize that. Okay, so just to get example 2 started, I've just defined the two functions. And if you want to continue with this, please pause the video and just carry on and just check your answers with the video when you're ready. Okay, there's no reason to wait while I'm doing it. Okay, if you're happy with the idea. So to differentiate dy, or to find dy by du, of course, we have to use the result from the previous lesson. So the derivative of cosine is, of course, negative sine. Okay, and this is with respect to u, so that's going to be negative sine u. Okay, so that's a standard result now, something that you'll need to know. And then du by dx is, of course, just going to be the derivative of 3x, which is, of course, 3. And when we compose these together by multiplying the derivatives, we get dy by dx as dy by du. Okay, multiplying du by dx. Okay, for reasons which we've already established. And so that's going to be the product of negative sine u and 3. Multiplied by 3. And just make this look a bit neater. So we don't usually leave the constant on the right-hand side when there's a trig ratio involved. So that's going to come to the front. So that's going to be negative 3 sine u, and then we substitute the u back in. That's going to be negative 3 sine of 3x. All right, so that appears to be the result for that one. And you can probably anticipate what's going to happen in the general form without doing it long-handedly, okay? But I would just like you to verify this if you want to using the chain rule. But the more general form, if I wanted to differentiate cos kx, I would let y equal cosine of u and u equal kx. And without doing too much extra work, you would very quickly find the derivatives would match the previous example. So dy by du would be negative sine u. Du by dx would simply just become k because it's a constant. And when we combine the two together, dy by dx, that's going to give us negative sine u multiplied by k, which is, of course, negative k sine u, and then again substitute the u back in. So that's going to be negative k sine of kx. All right, so the pattern's holding, isn't it? Yeah, it seems to be working. Again, if you just practice a few more examples, just changing these coefficients here, and just to make sure that you're happy with the result. Now, continuing on to example 3, once again, I'll reiterate, if you want to do these as an exercise and just check your solutions with the video, please do that. Okay. So let's have a look at how to differentiate e to the negative 4x now using the standard result and the chain rule. So we just define our functions as y equals e to the power u. Okay, this is kind of the tricky bit, isn't it? It's thinking of what the compositions might be. Okay, but you know that how to differentiate e to the x, and it's this part that's standing in the way, so that's got to be your substitution. So therefore, as well, the u function has to be negative 4x. So let's apply the chain rule and see what happens in this situation. So let's differentiate y. Now, standard result for e is really nice because it doesn't change whatsoever. It's going to be e to the power u. And the negative 4x is, again, really simple derivative that we learnt last year, du by dx. And we just we keep the constant, we keep the coefficient, and the x part disappears. So those are the two derivatives. And when we compose them together, what do we get? Well, let's have a look. So we get dy by dx is going to be dy by du multiplied by du by dx. All right. So dy by du, that is going to be e to the u multiplied by -4. So once again, we don't want to leave it like that. We can bring the -4 as a constant at the front. I keep saying constant, as a coefficient, I mean, e to the u, and then we substitute the u back in to here. So remember, we defined u up here as -4x, so that needs to go back in. So let's put it all together now. So this is going to be -4e to the -4x. And once you've seen one, you can probably anticipate what is going to happen when we generalize the result over on the right-hand side. So as an exercise, if you haven't done so already, just go through example 3 again, make sure you understand it, and then try to generalize the result. Okay. Right, now let's just have a look at the general form. Okay, I'm not going to go through all the steps again because we've done this several times, but just verify that if you wanted to differentiate e to the power kx like that, the result is going to be quite simply k e to the kx. So there is some similarity, isn't there, between the rules you learnt last year in differentiation and these unique rules. So these idiosyncratic rules particular to like trig functions or exponential functions. They are all slightly different, aren't they? But simple and sort of elegant in their own right. So all that seems to happen with the exponential function is the constant multiplying the x drops down to the front, and then the rest of the function is just retained. Okay, there's no change whatsoever. So that's the exponential. So we have another standard result that we can use. Okay, now example 4, I would like you to complete as an exercise, and I will go through the result in a minute. Okay, so let's have a look at this. And I don't know why I said in a minute, because this is a video and it's pretty much instantaneous, isn't it? Unless you pause it and go and have a cup of tea or do something else. So let's have a look what you may have got. Hopefully you got a result here. That looks good. So think about what the two functions are going to be. So first one, it's the natural log, that's the main thing. And what is substituted into it? Well, the thing that's making it look difficult is the 5x instead of just x. So that gives me my composition. So it's going to be the natural log of u, okay, and therefore u is going to equal something else, so that's going to be 5x, like that. Okay, so we differentiate these separately. You can still call them 1 and 2 if you want to. It's completely up to you. Sometimes I do, sometimes I don't, okay, but I always have four pieces of work. So the function y, the function u, and then the two derivatives. All right, so dy by du. Okay, now again, a standard result, which you may have seen the proof of. Don't worry if you haven't. So that's just going to be 1 over u. Quite surprising, that one. Okay, and for the derivative of u, du by dx is of course going to be 5. Okay, now we compose both of these together and we can generate dy by dx. So therefore dy by dx is going to equal dy by du multiplied by du by dx. And when we multiply these together, this is going to be 5 over u, isn't it? So it's the 5 we got from the du by dx multiplying 1 over u. So in other words, 5 over u. Okay, and substitute the u back in. Don't leave it in terms of u. So u, as defined here, was 5x. Okay, so this is going to equal 5x over, no, that's wrong, apologies. Try again. It's going to be 5 over 5x. Now notice what happens here. This is why we've got to be careful. We get the 5s, which will cancel out. So they will reduce down to well, it's going to be 1 over 1, isn't it? So we get the 1 over x back. So what's quite interesting about the natural log is it seems to be that even if you have a coefficient multiplying the x, it doesn't matter. You still get 1 over x as the gradient function. Okay. Now you can verify this on the right-hand side in the general form. So be careful with the natural log because it's probably not what you'd expected. And if you rush into it and say it's k over kx, that's fine because the k's will cancel, but make sure there's no k's involved. So the general result, and I'll leave this for you as an exercise, for d by dx of the natural log of kx, you're going to get 1 over x again. And if you left it as k over kx, just remember, of course, that there is cancellation involved there. Okay, so I just want you to be aware of that. All right, and example 5, we're saving the best till last here. This is not straightforward, okay, and I'll go through this carefully with you. We want to differentiate a to the power x, where a is a positive constant. So this is any kind of power, okay, exponential function, we should say. First thing to do is just as always, we'll say that y is equal to a to the power x. Okay. Now, on the face of it, we can't differentiate that using any kind of traditional. When I say traditional, I mean year 1 techniques. We can't bring the x down to the front. That's not how it works because it's not a constant in the power. It only works for polynomials, and this is an exponential function where the variable is the power itself. So we need something else. Now, if you remember from the first sheet on this lesson at the start, just before the warm-up, I gave you some key piece of information that you might need. One of those pieces of information was this, which I'm going to write down. It was the inverse functions, the exponential function and the natural logarithm. Now, when you compose those two things together, it's as if nothing has happened. Okay, so why is that useful? Well, we can replace the x. So that's how, well, that was how it was given at the beginning. It was posited to you like this, as e to the natural log of x is equal to x. But I can call that variable anything I want. So I could say, well, e to the natural log of, let's say, y must be equal to y, okay? In fact, let me put that in red as well so it's more clear. So that's going to be y also. Yeah, we can call that variable whatever we like. And you'll notice that I've defined y in this question already. Y equals a to the power x. All right, so let's move on. Let's carry on with this. So I can now replace the y with the a to the power x as stated right here. Okay, so I'm going to replace the y's with a to the power x. So let's do that. So we have e to the natural log of a to the power x must equal a to the power x. And you'll be thinking, why are you doing this? You're making it look worse. Well, It will help us, trust me. So we've now got this situation. You'll also hopefully remember that when you did laws of logarithms back in year 1, there was a really nice law that made life really, really useful and was the key to solving logarithmic equations. And that law was the power law. Now you'll notice on the left-hand side, we have an x in a power, but we also have, so it's a power within a power, isn't it? It's they're nested powers or telescoping powers. If you have an x in the power, we can use the law of logarithms to bring that power down to the front where the log is stated. So in other words, let me just write down that law for you from last year. So if you have the log of some base a, for example, let's not call it a, let's call it something else. Let's call it log to the base, I don't know, b. Okay, of some, and we'll have a to the power x as we've got there. Okay, that means that the law of logarithms states that that is exactly the same as x multiplied by log to the base b of a. Okay, so what has happened is that the power has been moved from the power itself, and it's now not a coefficient, but it is now become a product, okay, which enables us to solve exponential equations. So that's the same thing as what's going on over here. Now, the log to the base b, I could just call b, log to the base b would be, if b was equal to e, the exponential, that would be the natural logarithm, wouldn't it? So I can just as easily say, all right, well, if the b base was equal to e, then this is called the natural logarithm. So we now know that ln of a to the power x is equal to x multiplying ln of a. All right, and that's exactly the situation we've got here. Okay, so I can now replace what I've got on the left-hand side. I've now got e, and the x comes down to the front. So that's going to be x log a is equal to a to the power x. All right. Now, the base as well is just a number, okay? And if you take the log of a number, that's also just a number. So that means that this ln of a is just a number. So we've essentially got e to the power of some number multiplied by x now, which is essentially the same as e to the power 2x or e to the power 3x or whatever it is. It's the same idea. So I can now use the chain rule, which is really useful. So let me just get rid of all this, just so we've got a bit of space. If you're not happy with that, you need to revise your logs and exponentials work, is my recommendation to you. So therefore, we can now say that y, rewritten in a completely different way, but equivalent, is equal to e to the power x log a from that work we've done on the left. So what are my compositions going to be? Well, y would be equal to e to the power u, which means that all this here is going to be what my u is. Okay, so u is going to equal x log a. And we differentiate these. Okay, so dy by du is just going to be e to the u. There is no change there. And this is where we've got to be careful. In this right-hand equation, we have got log a multiplying x. And I've just said that natural log of a is just a number, okay, like 2 or 3. So if we differentiate u, with respect to x, which is what we've got to do here, we're going to be left with the natural log of a, because it is just a constant multiplying the x. And you know what happens when you differentiate a constant multiplying x? The x part goes. We can now find our derivative. So dy by dx is the product of these two derivatives. So it's going to be e to the u multiplied by the natural log of a. In other words, substituting the u back in, it's going to be e to the u, which we defined earlier. Where is it? Here. E to the x log a let's write that in, e to the x log a multiplied by the log of a. Now, that also looks really complicated, doesn't it? But this is where it gets even better. Remember what we defined e to the x log a as. Okay, there it is. It's just y, isn't it? And y is a to the x. So all that is just going to be a to the x multiplied by the natural log of a. I mean, that is such a nice result. I don't know where to start, really. Okay, it's a really, really nice result. So you've got the derivative of an exponential function is the exponential function itself multiplied by the natural log of the base. Now, before I get on to the general form of this, there's just something I'd like you to ponder. Let's consider the exponential function e, okay? So suppose we differentiate e to the x. Now, this is just, we know what the result is because we've done it. We know it's just e to the x, don't we? Okay, it was one we've worked on already. Really nice and straightforward. But remember, of course, that e is a base, okay? And it's a special base whereby the derivative is the same as the function you started with. So i.e., it's just so e is a special case of this. Okay, so if a was equal to e, what would happen? Well, we would get this. So you would get d by dx of e to the x would equal, using this result that we've just found, this result here. So you'd get e to the x back multiplied by the natural log of the base. Well, the natural log of the base is, of course, e. And what do we know about the natural log of e? Well, these are inverse functions, aren't they? Okay. The natural log of e is just going to be 1. So we get e to the x back. Okay, so e to the x is just a special case of all this. So again, as an exercise, see if you can differentiate a to the kx. And let's see what the result is in a moment. Okay, and just to conclude this, I've just started off with y as a to the kx this time, and using the inverse functions e and log, which essentially cancel each other out, I can now write y as e to the natural log of a raised in turn to the power kx. Now, also using the laws of logarithms, we now know that that is exactly the same as e to the kx, bringing the kx down, multiplying the natural log of a. And just to reiterate, I'm going to say it again because it's really important. The k and the natural log of a are just numbers. All right. So there's nothing to worry about there when we differentiate it later. All right. So that's what y is equal to. So I'll just put that as y is equal to all that. Now then, we've now got to create our composition, our composite functions. So y is going to equal e to the u, because we've no choice really. And then u is going to have to equal all the mess that's left over. So that's going to be kx log a, like that, which looks horrendous, but it's actually not. Okay, most of that is just a constant. So let's differentiate. So we'll call this one 1. We'll call this one 2 if you want to. Completely up to you. So dy by du is just going to equal e to the u, and du by dx, well, it's x to the power 1 again, and the constants in this are k and the natural log of a. So we're just going to be left with k multiplied by the natural log of a. There we go. Let's put it all together now. So dy by dx is going to equal e to the u multiplying k log a, and we can replace e to the u with e to the, just define what, or just review what u is again. It's up here. There's u, so I'm going to put that in. That's going to be kx log a. And all that, remember, is written here, which can be represented like that, which in turn can be represented like that. So they're all equivalent, aren't they? It's just y, essentially. So that's really good. So I can just write all this as a to the kx multiplied by k log a. Okay, so it's slightly different, isn't it? So that's the derivative. Just to make it really clear now, the derivative of a to the kx is this. Okay, so these are general results that we can now use. Okay, and just to conclude this section, and before we move on to the worked examples, I just want to show you a different way in which the chain rule can be represented, and it's something you might see in the formula booklets, okay, or a textbook. The function you're trying to differentiate, remember, is a composition of two functions, as you can see here. So the outer function is f of x, if you like, and the inner function would be g of x. All right, but when we write the compositions, of course, the g of x, because it is substituted into the f of x, results in two separate functions. So we would say that y is equal to f of u and u is equal to g of x, like that. All right, but there's no difference between what we've just been talking about and what's on the screen in front of you. So we can now differentiate with respect to u on the left-hand side and with respect to x on the right-hand side. And we just use the derivative notation for functions. Okay, so it's f dash and g dash. And then when you put it all together, as you can see, I'll just do that step for you. You get dy by dx. Okay, it's going to be dy by du multiplied by du by dx. Now, when you do that as a first instance, you're going to get f dash of u. I'll just put that in green. F dash of u, okay, multiplied by du by dx, which is g dash of x. All right, now u was obviously defined as g of x, which is here. So you substitute that in. So then you get f dash of g of x. All right, multiplied by g dash x, and it's just written as a product without the multiplication symbol. So that's where that comes from. It looks worse than it is when you see it at face value, okay? But it's just another way of representing the chain rule. You'll find that the chain rule is easier to use in a non-abstract way, just when you're in in a question and you're using it, it's fine. But when you see it written down, perhaps in this form, it can be a little bit off-putting. But I just wanted you to be aware of how some textbooks and formula books present it. Okay, so next we're going to move on to the worked examples.